We were talking about different kinds of capillaries, and we were talking about continuous and fenestrated and sinusoid. And then I was describing for you that the blood-brain barrier is slightly different. Now I've got a picture of it, so I just wanted to share that with you. Over here on the lower right, you can see that this is a continuous capillary that has an extra layer of cells that are covering these different leaky points inside of capillaries that are in the brain. So it is a continuous capillary, but these foot processes of the astrocytes are covering the areas that would be leaking. And so the blood-brain barrier, those capillaries leak less than a typical capillary. But let's talk about how capillaries are actually designed to leak. This is a bit of a wordy slide. I want to remind you that the exchange of stuff, remember, the cardiovascular system is delivering things and picking things up. It's a transportation system. And delivering things means not just driving around in your FedEx van on the freeway. It means getting to a house, stepping out of the FedEx van, and bringing a package to the front door, right? So that is capillary exchange, and that only happens at the capillaries. There are three different ways that things could get exchanged. If there were fenestrations, things could get exchanged that way. It can be that things can actually diffuse across. So there are some molecules that are so small, like carbon dioxide, that they can just move by diffusion. There are other molecules that are relatively large, like testosterone or estrogen or aldosterone. They're relatively large molecules, but because they are steroid hormones, they are hydrophobic. They also are allowed to move just by diffusion. We're going to be talking right now about things that need to move through the intercellular clefts, things that have to go through those spaces and how that happens. And so we're going to be talking about filtration and osmosis and reabsorption. All right, let's think about that. Remember that diffusion is the most important mechanism, but not because most things get transported that way. You could actually argue that most of the molecules that are actually being delivered or picked up are actually being delivered and picked up by the method we're about to discuss. However, the largest volume of things that's getting exchanged in an individual day get exchanged directly by diffusion, because most of the molecules that are actually being picked up are going to be molecules of oxygen or carbon dioxide. Now, we're going to be talking about these guys, substances that do not dissolve in lipids, molecules that are still not too enormous. They are going to actually be transported in the way that we're going to discuss. Remember that very large molecules, like proteins, like albumin, like fibrinogen, like platelets, like cells, those are things that do not leave those capillaries, not on a normal basis. The only time those things leave the capillaries is if you get a bruise or some kind of a cut. So we're going to be talking about this kind of capillary exchange, and I'm going to need you to remember a little bit about osmosis. Now, from my point of view, when I'm thinking about this, as I often am, I think about osmosis as a force where there are molecules, often large molecules, like albumin, that are requiring that the water come with them. So I think of osmosis as being a pulling force, like all of the albumin that's dissolved in your plasma, that is actually trying to draw water towards the albumin, bringing it into the capillary. So that's the osmotic force. The osmotic force is often referred to as colloid osmotic pressure, and it is a pulling force. Now, simultaneously, there is a pushing force. So, osmosis is trying to pull water into the capillary, bringing water back into the plasma. But blood pressure inside of the capillary is pushing against the wall of the capillary and is trying to push water and other molecules out of the capillary. All right. So we've set up a classic tug of war between osmosis saying, please don't leave water, and filtration trying to push the water out. All right. Opposing forces. Now, those opposing forces tell a much more complicated story than even this diagram can convey. Let us talk first about the force of filtration. Filtration, the primary source of filtration, is going to be hydrostatic pressure. And inside of this story, we're mostly talking about blood pressure. The blood pressure inside of your aorta was very high, right? It would go up to 110 millimeters of mercury. However, the aorta is not made out of leaky material. So it really doesn't matter how high the pressure is in the aorta, ain't nothing leaving the aorta. But when we get down here to the beginning of a capillary, there still is quite a bit of blood pressure that is trying to push water against the wall of what is now going to be the capillary. And here they say the blood hydrostatic pressure is going to be 30 millimeters of mercury. Okay, right? So that's just, let's just think of that as that's the amount of blood pressure that's left behind. It started out being 110, and as the arteries got smaller, it got smaller, and now we're at the beginning of the capillary, and we've got 30 millimeters of mercury left, and it is trying to push water out of the capillaries, right? Now, over the course of a capillary, blood pressure will decrease substantially. The reason why blood pressure decreases from here to here, you should not be able to intuit from this image. This image is not meant to explain to you why blood pressure goes down over the length of a capillary. That'll be a different image that we will look at. For this image, let's just go ahead and assume that it is true. At the beginning, blood pressure inside is about 30 or 33, and at the end, the blood pressure inside has dropped down to 10 or 13, okay? So the pressure pushing stuff out of the capillary has gone down. Remember, this is a tug of war, right? And what is opposing that pushing of the filtration pressure? It is the pulling of the osmotic pressure. At the beginning of a capillary, the strength of the osmotic pressure keeping the water, pulling the water into the capillary is only 20. So the filtration pressure pushing out is 33, pulling in is 20, out wins, right? In that tug of war, out is going to win. So actually at the beginning of a capillary, water and small molecules that are dissolved in the water, like sodium, like potassium, like chloride, like glucose, like insulin, water and small molecules dissolved in the water, that is actually leaving at the beginning of the capillary. And it is going to go splashing across these cells. And as it goes splashing across these cells, you can think of it as the mailman who got out of his truck and now he's delivering letters and packages to all the houses on the block. And while he's there, he's delivering some letters and then he's picking up some more letters. And as he picks up those letters, he's going to go back to his truck. He gets back in the truck and heads back to, let's say he goes back to the post office. So at the beginning, he leaves, delivers stuff. At the end, the water and all of the stuff that is still dissolved in that water is going to jump back in, because at the end of the capillary bed, the osmotic pressure that's trying to pull water into the capillary, it's still 20. But now the force that's trying to push it out Now it's only 13. So at the beginning of the capillary bed, filtration wins, water leaves. At the end of the capillary bed, osmosis wins, and the water and what's dissolved in it re-enters. So you should please remember that water and stuff dissolved in water will leave at the beginning of a capillary bed because filtration pressure is greater than osmotic pressure. And at the end of a capillary, water and what's dissolved in it rejoins the bloodstream because filtration pressure is less than the osmotic pressure. You gotta pause that, rewind it, write it down. That might be the phrasing of an exam question. Pretty close, right? Let's see. We're going to pick up this next topic at the beginning of the next video.